Hi guys, welcome to exercise 1. In this exercise, we'll topologically optimize a simple supported beam using bidirectional evolutionary structural optimization. Okay, let's get started. Just to remind you, we work with meters in Rhino, and firstly we need to create our initial domain that is simply a rectangle. Let's create a rectangle using rectangle component, and to specify dimensions we need to give a domain for x and y coordinates. So let's do it. Let's construct domain. This is this component, construct domain, and let's plug it to x, and let's copy it and plug it to y coordinate. And as a default, as you see, we have 0 to 1 rectangle, but we need to create our specific domain. Our beam is supposed to be 2.4 meter long and 40 centimeters high. That's why we need to plug in half of these values in one direction and using negative the same value in opposite direction. In this case we have 2.4 meter long beam, and now we can copy these two components and plug it to y, but this time we need just 20 centimeters, so in total we end up with 40 centimeters. Okay, and this is perfect. For Karamba we don't need just a boundary, we need a surface that will be meshed afterwards. So let's create a surface using boundary surfaces. Here we go, this is our surface, our initial domain. I will just create a connector component, surface, and we could give it a name, plate surface. And now, before we convert it into a real mesh and plate for Karamba analysis, I would like to find the points that will be our initial points for supports and the point where we apply the load. And we need to extract firstly these corners of our rectangle. We can do it in many ways, but one of probably the easiest is using discontinuity. So it basically extracts corners from our rectangle, and as you see we have our 4 corners. And now we need to find specific points in this point list using list item. We just plug this in. As initial we just have the 0 index for our point, this point, but let's just click a plus here, and in this case, in this way we can extract different points and just choose them. So our first point actually stands for support A, and let's give it a name, support point A, and let's copy this component, and the second point should be our second support point, support B. And if we want to find this point, we could just simply take average of these 2 points, so those 2 remaining points out of list item. I will just use average component and plug with shift these 2 points. Also let's give it a name, load point. I will just group these components, they stand for our geometry. This is it, that is ready to be now translated into Karamba elements, Karamba components, Karamba instances. Let's start with a plate surface. We need to firstly mesh this surface into finite element mesh. And Karamba has already a native component that does it for us, mesh breps. We can plug in open brep or a surface here. And as you see, it already created a mesh, but this mesh is pretty rough. The current resolution of the mesh is 1 meter. If you cannot see the mesh edges, you can always check this in display, preview mesh edges, enabling or disabling this option. And for our purposes, we need quite finer mesh than this one. Let's go to resolution of 1 centimeter. So 101. And now if I zoom in, you can see that our mesh is quite accurate. And now we need to create a plate, so we use mesh to shell component. So plate is a flat shell basically. And here we can specify a few options like cross-section, but we'll come back to this later. For now, let's continue with creating our other elements. I always create connectors at the end, so when we finish one stage of our design. So let's put this in our connector element. So at the end we have also a list of different elements that are ready to go to assembly. So let's start with creating supports. For that we need support Karamba. And the first point is our A. This support cannot move in this direction, and of course, because this is a flat plate, we need to also lock the translation in Z direction. Let's lock these three components, a free condition, degrees of freedom. And also for Karamba, because it's a flat plate, we need to lock the rotation around the axis that is perpendicular to our plate. In our case, it's RZ. And then for the second support, we can just copy that and plug our B. But in this case, we need to unlock translation in X direction because our support can move like this. This is conditions for simply supported beam. And now I can create again using parameters our connection component that is support. And with Shift, I'll plug these two supports here. And now it's time to create a load. For that we have a specific component called loads. As a default it's a gravity, but when we click to this drop down the menu we can choose different options, and for now we need a point load, and to specify our point load we need a force and we need a position. So for the position we have already our load point here, perfect, and now the force should be going in Y direction. And this force in our example I showed you in the presentation was of magnitude 100 newtons. Force in Karamba is specified in kilonewtons, so when we multiply 100 newtons by 10, because this is how we enlarge our design, it's 1000 newtons, so this results in exactly 1 kilonewton. Don't forget that our force should go into negative direction. So I will just plug this negative between Y and force. And also again at the end let's create a load param. I will start making a group out of this that are all Karamba elements that will go to assembly. But this is not the end. We need to specify two more things. Firstly, cross section. And again, this is a huge component that we could specify any cross-section we want. And choosing from drop-down menu, we should use shell constant. So basically it's for shells with constant cross-section, and for height we just use 1 centimeter, again referring to our case study exercise. And again, I will create our param. And I will add it to group. And one more thing, it's a material. So we go to material selection, and we could specify our own material, our own concrete properties. But for now, let's go with default values for concrete. And let's see how this works for us. And again, I will create a parameter material, plug this here and add material to our group. And now it's a very important step, that is assembling our model. Assembly model. And what we have here, we need to specify elements. So I'll go to elements. If you have more than one element, always flatten at the entrance. I have two supports that are in one list, but in case there are three, always we should flatten at the entrance. And loads is also just one load case. Then we have cross section that goes here and the material that goes here. And this looks like ready for analysis, but I would like to show you one more thing. Let's plug model view to our model. And this enables us to check if we specified our boundary conditions in the right way. As you see, the supports look pretty big, so I can just go here and check the scale of our display to just make them a bit smaller so they look more realistic. And this looks quite fine for now, but there is one issue, that we didn't select these points out of our initial mesh that we created. These points are just points from initial geometry. And in case of this high resolution, it works pretty well. We have no bug here. But if I change my resolution to, let's say, 5 centimeters, 5 centimeters actually works, but if we go to 4, it also works. Okay. So it depends on how we subdivide our mesh. We could have this error. And you see that it cannot find the point load. As you see, these points for corners, they're exactly lying, always doesn't depend on resolution of our mesh. They belong to a mesh, they lie on our mesh exactly, but this point in the middle, as you see now, it is exactly in between our triangles. Probably with 4 it's exactly here, so it works, but with 3 centimeters the resolution didn't work out and it gives us an error that we cannot find point load, this point in our overall mesh. And to fix it so it works in any case and any resolution for the future, we need to make sort of a trick, but it's very important both in Kangaroo and both in Karamba. We always need to find points that are belonging to our mesh that we are using. So I will use point params and I will plug this and I will give it a name all points. Okay? I will copy this and create a connection and wire display hidden. It's just for visualization purposes that we don't have too many cables. We can turn on the preview. And we need to make a simple trick that is use find similar member. And that finds for us, we search for this point in the group of all points, and I plug this instead of point directly to our support. And let's do it for the other support. So I plugged my point B, and then point found in the mesh goes to my support. And the same thing for load. So load point goes to D and edge goes to position. And now we should fix this problem. If we zoom in, it finds the closest point sort of arbitrarily to right or left of this initial point that was in the middle. So if you want to see a difference, this is our initial point that could not be found, and this is our point that is the closest to this one, and it works for Karamba quite well. I will just come back to our resolution that was working perfectly, 1 centimeter. This is just in case you want to play with different resolutions or you change the domain, so we just make sure it always works. And I will make the last component, connector component, that is our model, ready for analysis. And I will make it red. For your information, all the components that will be finishing one part of the exercise are always marked in red, and we start the next part from this component. So this is definition for now. We created geometry and created an assembly model for Karamba analysis, and see you in the second part of this exercise. Thank you.